Hi folks, this is the video for Operations Research, Deterministic Operations Research, the video for deterministic inventory theory to cover while I'm out. So we had finished in the last class the case where we had continuous review model where we were not allowing shortages and we had an instantaneous arrival. We talked about the weaknesses of those assumptions. And what we're doing, just as a reminder of that from the last class, what we had was that the optimal order size, Q star, was equal to the square root of 2dk divided by h, and the optimal cycle time, which is equal to Q star over d, works out to be the square root of 2k divided by dh. Again, where d is your demand rate, k is your order setup cost, and h is your holding cost. So before we move on to dropping one of the assumptions in this economic order quantity model, just a little reminder in terms of how things relate with regard to these values. So first off, what happens if K increases? So if the setup cost increases, what would happen to the values of Q star and T star in this case? So the idea here is if you're paying more for a setup cost for each order, sorry, I should have put an equal sign there. But if K star is increasing, then basically what's happening is the cost of ordering is increasing. And because of that, you're going to want to order less. So, sorry, when I say order less, I mean order the same amount but in fewer orders. So because of that, when K increases, what's going to happen is that Q star, your order size, will increase because you're going to order fewer times, but you still need to order the same amount over that longer period. And if your batch size is increasing, then also T star is increasing because you're going to go longer in between orders. Okay. Now, as far as D increasing, the demand rate is increasing. So when that happens, and again, just like a lot of these other things, we're saying all of things remaining constant. So if you have higher demand, then obviously you have to order more. So Q star is going to increase. And again, as far as this is concerned, well, will T star increase? Maybe, maybe not. It really depends upon how much you're ordering. So it really comes down to how much Q star increases relative to how much D increases. So T star could go up, down, or remain the same. Oftentimes it ends up going down, and you can certainly take a look at that by taking a look at the derivative of this, but and that's something you're going to have to do with regard to the homework. Okay. Now, the holding cost. What if H goes up? Well, if H goes up, it costs more to have things in inventory, so it should make sense that you're going to order in smaller batches. So Q star is going to go down. And since Q star is going to go down, but the demand rate has remained constant, then T star will also go down. Okay. So that's the basic set of relationships here. Again, we can get specifics by taking a look at derivatives, by taking a look at the behavior of these functions for specific types of changes, and like I said, you have that in one of your homework problems. Okay, so the next piece here is to add planned shortages. So first off, if we're talking about planned shortages, one of the questions that comes up is, when would one want these, or want to use these? Well, there are a couple of basic reasons why. First off, the customers are willing to accept a delay. If you remember, with some of the new cars that have come out over recent years, certain cars people have been willing to wait for, as opposed to going and buying another type of car. So there were certain car companies, I believe Honda was one of the recent ones, as well as Nissan, where instead of having to keep extra stock, customers were willing to go place an order for the car, and it would show up a couple of weeks later, sometimes a month later. But that said, that's basically being willing to accept a delay. The second one is essentially that the shortage cost associated with those shortages is not greater than the cost of holding more inventory. Certainly, if holding inventory is very, very cheap, it may end up being that they go ahead and hold more inventory and not have a planned shortage, or they may not have as big of a planned shortage. Okay. Well, remember the graph that we did in class last Thursday? We have a similar type of diagram here to look at the relationship between inventory level and time. Here's inventory, here's time, and what we're going to define here, a lot of the stuff is stuff that we've had before, but for the purpose of this graph, we're going to define S to be the inventory level after Q units are added. So we get our batch, we fulfill the back orders, and S is what's left over in inventory after we fill the back orders. So this is going to max out here at S. It's a constant withdrawal rate, just like we had in the previous EOQ model. But what's going to happen is that this is going to dip down below the horizontal axis. This area down here corresponds to shortages. The equation here is S minus dt. Before we had Q minus dt, but we've got a different intercept here. The order is placed, and we go back up to S. So the vertical distance from here to here is Q. our cycle length, just as before, is Q over D. But the quantity right here, the time frame right here, is S over D. So at time S over D, we run out of inventory, and the difference between these two is the amount of time during which we're taking back orders. This process continues just as it did before. So this is 2Q over D right here. But in this case right here, we have a full cycle. And the cycle from here to here started at S over D. This distance is Q over D. So this is S plus Q over D. And in future cycles, we add a multiple of Q to this to figure out the future points when we run out of inventory. Give you a moment to finish that. Reminder from the last class, lowercase p here is your shortage cost. And again, this is per unit time. And the quantity Q minus S is the shortage before the shipment arrival. So just as before, we're putting together a cost function here. The production cost or the ordering cost hasn't changed per cycle. It's still K plus C times Q. The average inventory level. As far as the average inventory level is concerned, we're worried about this from the standpoint of holding costs. So we really only have to worry about this while we have inventory. So our maximum inventory is S, our minimum inventory is 0. We have a uniform drawdown over that period, so it's going to be S over 2. And hence, the cost per unit time is going to be HS over 2. So our holding cost, just as before, is going to be a cost per unit time times our cycle length while we have inventory, which is S over D, and so this is HS squared over 2D. For the shortage cost, the time during which we have shortages, so the cycle length when when shortages occur, is going to be Q minus S over D. And so our average shortage level is going to be Q minus S over 2. And our cost per unit time is P times Q minus S divided by 2. Just as we did with the holding cost, we have to multiply this by the cycle length while shortages occur. So we're going to take Q minus S divided by D and multiply it by our cost per unit time. And as a result, the shortage cost per cycle works out to be P times Q minus S squared divided by 2D. Okay, so as we did in our simpler model, we're now going to put our values together here to get the total cost per cycle. We'll also get the total cost per unit time. So the total cost per cycle works out to be K plus C times Q plus H times S squared divided by 2D plus P times Q minus S squared divided by 2D. So our function per unit time is capital T again, and this is going to be a function of both Q and S. We can choose our batch size, we can choose our shortage size, our planned shortages. So what we're doing here is we're taking the total cost per cycle, and again, we're going to divide by the cycle length. So we're getting this by dividing by Q over D. And if we do that, we get this to work out to be K times D divided by Q plus D times C plus H times S squared divided by 2Q plus P times Q minus S squared divided by 2Q. So again, our goal here is to minimize total cost per unit time. Like I said before, this is in the last class, this now is a Calc 3 problem instead of a Calc 1 problem. So what you're going to end up doing here is taking the partials of T with regard to Q and with regard to S. We're going to set those equal to 0 and solve simultaneously. The work is shown in the book. I'm not going to recreate it here. You can go ahead and look through that. Good practice on your partial derivatives. But when you do all of this and end up solving for S star and Q star, what you get is the following. Q star works out to be square root of 2dk divided by h times the square root of p plus h divided by p. As far as S star is concerned, it works out to be the square root of 2dk divided by h times the square root of p over p plus h. As a result, we also get little t star is still q star over d. That works out to be square root of 2dk over p times the square root oh, sorry, my goof, wrong line, 2k over dh times the square root of p plus h divided by p. And then q star minus s star, so this is going to be the maximum shortage, the optimal maximum shortage. This works out to be the square root of 2dk over p times the square root of h over p plus h. Now, some of the behavior to understand here in terms of things going on, and we've got a couple other formulas to look at, but actually just one more. But if your holding cost goes up relative to your shortage cost, then it should make sense that you would want to take larger shortages. And as you can see here, if P remains constant and H goes up, this ratio is going to get smaller. And more importantly, this quantity is also going to get smaller, so S star is going to get smaller. And when you think about the intercept on that graph, it's going to move closer and closer to 0. On the other hand, if your shortage cost gets larger compared to your holding cost, then it should make sense that S star is going to get larger. And so we're going to want to have fewer shortages. Okay. And it may be easier to see that right down here with Q star minus S star. If H is remaining constant, P is getting large relative to H, then this quantity is going to move towards 0, so your maximum shortage is going to get closer and closer to 0. Okay. The other thing you may have noticed here is that as far as the term Q star is concerned, as far as the term T star is concerned, the first piece of each of these products is what we got in the economic order quantity model, where we had no shortages. And making that change in the assumption essentially means that we're multiplying those original values by these square root terms to figure out what the new values are. Okay. The other term that I said we hadn't put up yet, we need to mention, is the ratio S star divided by D over Q star divided by D. Everybody in this room can, well, sorry, everybody watching can do this algebra, and everybody in this room can do it too, because at this point I'm the only one in this room. Anyway, so, but as far as this is concerned, the way to think about this is that this is equal to the fraction of time without shortages. And if you do the algebra, what it works out to be is P over P plus H. again, if you look at behavior here, if P is getting very large relative to H, then this fraction is getting closer and closer to 1. If the shortage cost is very high relative to the holding cost, then we're not going to want to incur shortages, and that's what that's saying. On the other hand, if H is getting very, very large relative to P, that is holding costs go very high relative to shortage costs, this is getting very close to 0, or it's getting closer to 0, and we're willing to deal with shortages the majority of the time. So, if we go back to the problem we were working on last time, what we had here for this one is that our demand, actually I think these numbers are different than the ones I had in the last class, but the demand that I've got here is 600 units per year. K is $25, our setup is $25. Our unit cost is $3. Our holding cost, I have to check my units on this, I'm sorry. Yes, this is not per year, this is per week. H is our holding cost, it's 5 cents per unit per week. And for this one, our shortage cost is $2 per unit per week. So again here, if we do our plug and chug, S star works out to be the square root of 2 times 600 times 25 divided by 0.05 times the square root of 2 divided by 2 plus 0.05, and that works out to be 765.09 units. Q star, that's the square root of 2 times 600 times 25 divided by 0.05 times the square root of 2 plus 0.05 divided by 2. And this works out to 784.219 units. If we work with the assumption that the units are divisible, then what we have for T star is the square root of 2 times 25 divided by 600 times 0.05 times the square root of 2 plus 0.05 divided by 2. And that works out to 1.307 weeks. And hence Q star minus S star is equal to 19.127 units. Like I said before, if the units are not divisible and we have to work with integer orders, we're going to use standard rounding rules here. So we would end up with 765, 784. Turns out that with the rounding, it's still the Q star minus S star still works out to be 19. Our T star would change ever so slightly here because you would have to take our Q star, which would be 784, and divided by our demand, which is 600, and so T star would go up ever so slightly. One thing to notice about this problem, something I mentioned earlier when we were talking about all the relationships, we don't have much in the way of planned shortages here. If you think about this in terms of the overall order size, we're only talking about 19 out of 784, so we're slightly between 2 and 3% of the total cycle usage of orders in terms of our shortfall. And the reason that that should make sense, when you think about it, our holding cost, sorry, our shortage cost up here, $2 per unit per week, our holding cost is 5 cents per unit per week, so our shortage cost is 40 times the level of our holding cost, and hence it would make sense that we're not going to want many shortages, and that's what works out here. So, as I said before, we can see that that's what's going to happen here. Okay.